All right. So, uh, hello everyone. Welcome to Low Power and UPF session. This is Rohit Sinha from Intel, and I am your session chair for this particular session. And just a brief history and background. I am mainly working in front-end design and methodology in Intel since 5 years, and I have around 20 years of experience in the industry. So, coming to our first paper title is Hierarchical UPF, a uniform UPF across front-end and SD, structural design. So our first presenter is Dipankar. Just a brief history about Dipankar. He completed masters in the field of VLSI design from Vellore Institute of Technology. Since 2017, he's been working as low power CAD engineer in Intel Corporation. His research interest lies in low power techniques, UPF, power aware verification. So over to you, Dipankar. Uh, can you play the video,
And
please?
welcome to this presentation. My name is Dipankar. I am from Intel. Together with my colleagues Balaji, Vishwanath, Aditi, Nigam, and Tahir Ali, we are going to talk about hierarchical UPF and its advantage across front-end and back-end. We will start today by talking about UPF and different types of UPF. Then we'll talk about their consumption across front-end and back-end environment. We'll talk about what are the advantages and limitations of these different types of UPF consumption. Then we'll move on to the POC done on hierarchical UPF, issues and learnings from the POC. Then we'll talk about the guidelines published for SOC team for the smooth consumption of this hierarchical UPF across front-end and back-end environment. Then we will finally conclude this presentation by talking about this overall summary and current status of this hierarchical UPF consumption uh, in one of the SOC project. The Unified Power Format or UPF is an IEEE standard. It was originally developed by members of Accelera and then donated to IEEE. It is a tickle-based standard which is intended to ease the job of specifying, simulating, and verifying IC designs that have a number of power states and power islands. UPF helps reflect the power intent of a design at a relatively high level. It is used to describe multi-well scenarios, meaning which power rails should be routed to individual blocks, and power gating scenarios like which blocks are expected to be powered up or shut down. It also helps in realizing how voltage levels should be shifted as the signals across from one power domain to another, and whether measures should be taken to retain register and memory cell contents if the power supply of a domain is removed. There are various ways of writing UPFs. These are hierarchical UPF, flat UPF, and merge UPF. The expectation here is the audience present for this session are familiar with the basic concept of UPF, such as a power domain, power supplies, level shifter strategy, association strategies, power switch, etc. So we are not going to talk into much details about them. Let's look into the different types of writing the UPF. Consider the design here. There is a block. It contains two supplies, VN and VDD. This block contains two instances of a child module, child 1 and child 2. This child module contains two sub-child instances which are on two different gated supplies. Hierarchical UPF is the bottom-up approach of writing the UPF. Here we can write the UPF for individual children blocks and then refer it in the parent blocks. For example, here we are writing the UPF for the child block, and then we are defining creating power supply beneath supply port, everything was a child block. And then we for the top block we are just referring this child UPF as with the scope child 1 and child 2. The scope here is the actual instance hierarchy of that module. This is the basic way of writing the UPF. Now let's move on to flat UPF. In flat UPF, all the UPFs are brought on to the same top level scope, and all the different UPFs are now merged into a single UPF. As you can see here, the child UPF which is present in the hierarchical UPF above is now part of this single concatenated UPF itself. Create power domain PD child 1 with the element child 1, which is the actual instance name of the uh, child block here. Now, what is the merge UPF? If two power domains in the UPF have same supplies, then we can combine them together into a single power domain. This UPF is known as merged UPF. For example, on the left, you can see that child 1 and child 2 are same are driven by same supply VDD. So in the merge UPF, we can create a single power domain for them instead of defining two separate power domain and have a simplified version of UPF. Flat and merge UPFs are often known as top-down way of writing the UPF. In this industry, most of the time the UPF delivered by IP teams are hierarchical in nature. Now let's talk about how these UPF files are consumed. This diagram here gives the high-level overview of how UPFs are consumed across SOC. So UPF files are written in accordance with RTL based on the power intent requirement. UPF together with RTL are uh, input collectors for synthesis, and this synthesis generates a UPF prime and netlist, and then this netlist and the UPF prime consumed for the floor plan and placement and route tool to generate UPF prime and APR netlist. In all these three main stages, UPF and RTL are together lint checked for any violation or wrong strategy, and each of this UPF, RTL, and UPF prime netlist are validated using FEV tool to make sure that they are functionally equivalent. So UPF RTL is matched together with UPF prime and netlist, and similarly UPF RTL are compared with UPF double prime and netlist, APR netlist. Now, let's look over the front-end UPF generation process. So we generate connectivity information from the RTL, and we have IP UPF for those RTLs as well. And based on the power intent, power architect input, we have a PSG table. So the UPF generator tools integrates those IP UPF, and according to the connectivity information, it generates the UPF. So these UPFs are hierarchical in nature, but because of the uh, issues in backend tools, which we'll discuss later, we cannot directly consume this UPF for synthesis and subsequent stages. So we uh, merge the IP UPFs based on the spec, like equivalent power domain, so on, and then we generate merge UPFs, and this merge UPFs are then checked, are validated to make sure that these are equal with the hierarchical UPF using the formal equivalence check. Then we run low power lint tools, and then these are handed off to the backend. The reason for using hierarchical UPF for backend implementation is because In the past, downstream implementation tools could not easily consume hierarchical UPF files. There were many limitations. Backend tools could not properly understand IP level power intent. Sometimes strategies were not properly realized and they were dropped. There are PST conflict issues also because of PSTs in the child UPFs. This results in dropping of PST tables, which in turn reflect a wrong power intent. Because of roll-up of IP UPFs in bigger blocks, sometimes the count of power domains are significantly higher. This used to cause severe increase in the runtime. Also, PDOI or power domain on instance routing between children blocks were always buggy in the APR tools. Now we have alternative solution available, so that is how we are able to move forward with hierarchical UPF. Another limitation was power intent of equivalent gated power domains were not been properly realized by APR tools in the past. Because of these limitations, backend flows require merged UPF files as they are easy and straightforward to consume. However, the generation of merged UPF files is a tedious task. It is done via a script that involves various configurations, and the process itself is buggy and often requires manual interventions. So the turnaround time for the initial setup of a block itself is around 7 to 8 weeks, as we have seen in the previous SOCs, and for any subsequent iterations, because of backend request, it used to take 2 to 3 weeks to completely generate the merge UPF flow and validate it. There is no industry standard tool available for generation of merge UPF because of the involved complexities. We cannot use merge UPF for the verification because verification requires selective enabling and disabling of blocks, and in merge UPF that is not possible. And to validate the merge UPF, there is only one way in front end. The way is to run formal equivalence check on this UPF. In this one, we generally give same RTL on golden device side and hierarchical UPF on one side and merge UPF on one side. This tool itself is not 100% accurate and we have seen some misses in the past. Only using gate level simulation we can conclude that the UPFs are completely equal. But this GLS simulation always comes at the very end of the project, so it is not very beneficial. Because of the complexity involved for the GPF generation and validation, we decided to do POC on using hierarchical UPF for backend implementation as well. If the POC becomes successful, it would be very beneficial for the uh, project and it will reduce the total turnaround time by a lot. So we decided to do this POC on a very complex partition. This partition actually contained equivalent power switches, isolation strategies of both parent and self location, enable level shifter strategies, and multiple soft IPs and hard IPs. In this POC, we ran all the tools and flows from in front end as well as in back end. And then we published the guidelines and learnings for the next project so that they can easily do the necessary change and consume the hierarchical UPF. Now let's see all the issues seen during our POC on the hierarchical UPF. So in front end, the low power static check tool, we saw no issue. Uh, During front end handoff synthesis, the previous chain synthesis tool was unable to insert isolation if the location was parent. We filed a ticket on the vendor, and also parallelly we tried out the next gen synthesis tool, and we didn't see the same issue there. And also we had to clean our UPF for missing CSN and had to apply the voltage value for all the supply nets. For the backend end of synthesis, we saw the same issues what we saw in front end of synthesis. During the APR flows, There were a few crashes initially because of incorrect buffer and inverter placement. Then we cleaned that up, and also to merge equivalent power domains and equivalent power switches uh, into one power switch or one power domain or voltage area. We got the command from the vendor and applied it in the design, and then we were able to proceed. During backend low power static check tool, we found one bug related to the shared voltage attribute which we used in during APR tool. The LP static check tool was unable to comprehend this option if it was used for multiple elements in separate lines. So we filed a ticket on the vendor and they subsequently fixed it. Also, there were many violations related to merging of power switches. We found them to be expected and waived them accordingly. In LVS, output nets of equivalent power switches, the example on the right, G1 and G2 nets are two distinct power nets and are not shorted by default. But in a single VA, we can either create uh, G1 power grid or G2 power grid. If the floor plan tool uses G1 as the primary power of the voltage area, the PD2 domain uh, cells will be logically connected to uh, PD1 domain nets, but physically connected to G1 supply. So this will create an LVS open. So there are two solutions for this. Either we use set equivalent command of the UPF to short this output supply net, or port this output supply net of the UPF to the parent UPF and short them out together. During RV checks, uh, reliability verification, we found no issues. For the low power FPV2, there were some violations related to merging of power switches, which were expected, and also there were many violations related to biasing, as our test case didn't have biasing, but we were using standard cells which had biasing in it. After our successful POC, we found out that the Hierarchical UPF has a separate set of challenges, but we could overcome them with strict compliance to certain guidelines. So we compiled all the learnings and published it to the SOC team well in advance for the easy execution for the upcoming project. These guidelines were like use of localized UPF was a must. Here we copy all the child UPF in a single directory because all the IP UPFs are scattered all across the servers. And then we replace the path with the normalized path of that directory. So this eases our process of shipping. And also the configs used in these IP UPFs become consistent. Also, all these IP UPFs uh, should be strictly compliant with the Intel-wide UPF 2.1 templates. We were not allowing mix and match of versions. We have seen issues in past by when we mixed different versions. Some tools were unable to comprehend the construct easily. Well wising should be done for all the supply nets present in all the UPF. Even a single miss will cause implementation tools to fail. There isn't any single rule in the NP static check tool to detect this. The value of attributes used in the set design attribute command should be consistent in all the UPFs. For example, if the UPF, for example, if the value of the attribute is true, in the topmost UPF file, the child UPF cannot have false value for the same attribute. Usage of deprecated and legacy UPF constructs can cause errors during synthesis. Some of the constructs like set domain supply net and extra supplies cannot be used along with UPF 2.1. Again, LP static check tool may not fail, but during synthesis, the tool will definitely error out. All the gated supplies from the IP should be ported out to the partition level. This is done to short the gated supply in case of equivalent power switches, and also to have a complete PST at the power level. And also we were adding protection around the add power state command and PSTs for all the IP UPF, and so this is to avoid the PST related conflicts arising during the implementation. So this means the topmost PST should contain all the legal combinations. We should do connect supply nets for all the ports and nets. Any missing CSN will result in failures in backend tools and violation in the LP static check tool. And all the internal supply nets should be brought to the partition level, because if you want to add fillers during APR on those nets, uh, we will not be able to do if we don't bring them out to the partition level. So to summarize, the POC done on the hierarchical UPF showed no major challenges or degradation in the quality of results. So we decided that the hierarchical UPF will be the POR for the ongoing SOC project, and they should strictly adhere to the guidelines and learnings we published. The initial bring up and integration of the front-end UPF took some effort for that SOC because many IP UPF files were not adhering to the guidelines, but till now we haven't found any showstopper issues and the execution is going on very well. This adoption has resulted in a significant reduction of the time and resources required to configure and generate and validate the equivalencies of the merge UPF with the hierarchical UPF. And we are also now able to directly consume the third-party IP UPF in the flow without doing any hacks or any merging. This has significantly simplified the front-end flows and turnaround time for the UPF integration, which is resulting in a saving of 8 to 10 weeks for the initial bring up uh, and 2 to 3 days only for the subsequent drops. Additionally, we can directly run the low power static check on the IP UPF files, resulting in very faster debugs and fixes in the SOC design cycle. This has also ensured that the basic principle of consuming same UPF files across the design is followed. Thank you very much, and now we can move on to Q&A.
Hey, great presentation, Dipankar. So I'll open the floor for the question. So I have the first question, Dipankar. So most of the challenges of the merge UPF, right, the bottleneck was mainly because of the implementation tool requirement and challenges and support there, right? So from the
Yes.
front end perspective, do you see any challenges if we continue with the merge UPF and you have the equivalence checking? Is there any such requirement from the front end sign off?
From front end, I mean, only challenge here is to bring up the flow. If the IP is third party UPF and it's not adhering the templates, right, the Intel wide template, then definitely I will not be able to run this merge UPF generation flow very easily. And to validate that merge UPF, generated merge UPF with this hierarchical UPF would be very tedious.
So if we need to go with the PST equivalence with the merge and the hierarchical in the front end, is there any bottleneck there?
No.
Okay, all right. So we have the another question. Dipankar, you can just answer those in the chat box.
Yeah. Uh, mm, I mean, one uh, from our execution, one basic challenge was like if the IP UPFs are in different UPF version, then consuming that UPF at like that UPF was very challenging, and definitely we saw errors with the APR tools there. And as such, there is no such mention of this in LRM that you cannot consume different version UPFs and all, but uh, and there were like many issues because of, I mean, there are many constructs present in the LRM which we cannot directly use for the hierarchical UPF consumption. So that is why we had to limit. We have a Intel-wide template which we strictly adhere and follow, so that the consumption is streamlined.
Okay. If there's no another question, I have one question. When you says 8 to 10 hour or 60 to 70% saving, right? Is it the front integration time saving, or it's the sign off saving in terms of low power checks or simulation like that?
It is the first bring up of this hierarchical UPF, right, for the entire SOC. Sorry, merge UPF for the entire SOC. Generally, definitely, you need to fix many issues because of construct. We cannot directly run our merge script on those high UPFs, right? So, initial bring up of the merge UPF flow, and then make sure you validate all the equivalence of the generated merge UPF with the hierarchical UPF. That's the main total time I'm talking about.
Okay. All right. Thanks. Any other question? Uh, you can put it in the chat box, or you can speak out here. We have 2 more minutes, then we switch to the next presentation. Or if somebody wants to share the experience with their company or industry, how is it working on, because this is a very interesting topic, right? So how's other company doing with merge UPF and hierarchical? Any experience sharing as well? Most welcome.
Excuse me, Pragya, this is Brandon. Actually, we have been dipping our toe in this water ourselves, and the reason I asked the question about the constructs is it was surprising to us when we tried to model a hierarchical UPF, really just how little of the language is useful, and in many cases you're resorted to explicitly porting pins to nets as opposed to taking advantage of some of the set equivalent commands. The biggest paradigm for me was talking to the back end teams and understanding that my understanding as a verification guy of a logical power domain versus the physical idea of that, and the fact that the LRM really didn't have a clear way for me to tag the IP scoped domains as being physically equivalent to the top level logical domain that I wanted to place them in. So it was an education for me as we've gone through this. So I think a great job by highlighting a lot of the issues. I think these are common things that we're running into, and let's continue to push this forward and brainstorm together. How do we make this easier as we go forward? Because we have to start abstracting, and we have to start leveraging verification down at lower levels, and to take advantage of a hierarchical representation, and then ultimately have to decide that we're better off merging them because of tool issues or because of language issues. We really can't handle that. We need to solve that problem.
Indeed. Thanks, Brendan, for sharing your experience. Yeah, there are a lot of LRM enhancement that is potentially that is required here. So yeah, all right. Thanks, guys. We will switch to the next presentation, and the title of our next presentation is title of the next presentation is path-based UPF strategy optimally manage power on your designs. And the presenter name is Progyna Khondkar from Siemens EDA. Just a brief history about Progyna. He's a low power design and verification expert. He holds 2 patents, and he's the author of Low Power Design and Power Aware Verification book, which is published from Springer. And he has numerous publication in power aware verification field. So yeah, over to Progyna. Please play the recordings.
Khondkar. I work for Siemens EDA. Today I'll talk about my paper, which titled Path-Based UPF Strategies, Optimally Manage Power on Your Designs. The first slide shows the agenda where I'll cover port-based and path-based UPF semantics for strategies, how path-based semantics actually works, why port-based semantics are ad hoc or inefficient, path-based ways to optimally manage power on any design. I'll talk about case studies with examples that will allow easy transition from a port-based to path-based standard methodology. At the end, there would be concluding remarks and references to this presentation. This slide shows the background of this presentation, where we will use isolation as an example for strategy. An isolation is required when the source logic goes off and sync logic is on, as shown in the middle of this diagram, where PDMP3 is a switchable power domain which is off and tends to propagate X from PDMP3 to PDDISP, where PDDISP is on domain. The isolation, which is symbolized as a green triangle with arrow showing up, try to prevent this X propagation. Here in the green strip, we show the isolation strategy semantics from UPF LRM. So we understand that if ISO is not inserted properly at right path, then it can lead to functional failure of the design. On the other hand, if ISO are placed at a location where it is not required, it could be redundant and could be potential risk of wasting area and power. In this slide, we will talk about port versus path-based semantics. In fact, UPF 3 and 3.1 combinedly introduces path-based semantics for isolation or other strategies in conjunction with dash sync and deep supply only true commands from UPF. These in combination explicitly defines paths from source to sync domain for these strategies. Before path-based semantics were in place, ISO, LS, or repeater utilizes ad hoc methodologies, such as port splitting, which could be very difficult to manage power, because when ISO are specified on ports and port fan out to multiple receiving logics, the port-based semantics would end up placing isolation cell in all paths. On the other hand, path-based semantic places ISO in paths that goes to specified sync or receiving logic. Because net splitting are relevant to the port and places ISO cell that goes to specific sync only. Eventually, it allows to optimally manage power on any design. But as you can understand, path-based methodology adoption are not straightforward. Depends on contents of strategies. ISO with location fan-out, self-parent could cause extra complexity to imply a strategy according to the expectation. In this slide, we will talk about how path-based semantics actually works. In order to do that, we adopted an example of isolation strategies for set ISO 1 with elements, ISO 2 with elements and sync, VDD2, which is the primary for PD2 power domain, and ISO 3 with elements and sync, VDDT, which is the primary of PD top power domain. So we see the arrangement where PD1 have an isolation cell outside of its port, and in addition, there are ISO 3 and ISO 2 based on this isolation strategy. We can also understand immediately looking at the diagram, the fanouts cause ISO 1 to sit on both the path for ISO 3 and ISO 2. So evidently, we can understand ISO 1 is redundant. And also based on UPF LRM, it has lowest precedence. Whereas ISO 2 and ISO 3 have same precedence because they are covering different things and different paths, hence they have no conflict. So tool must drop ISO 1 due to a lower precedence or redundancy, and tool must honor ISO 2 and ISO 3. Each cases of ISO 2 and ISO 3 cell must be placed as close to sync domain possible. Because path-based semantics promotes net splitting, this will help to facilitate the placement. In addition, path-based semantics also applies isolation strategies per path basis. Net splitting helps minimizing collateral damage. We will talk about collateral damage in the next slide with port-based semantics example. Now coming back to this slide, for path-based semantics, when location fanout is specified, target insertion port must be on target domain boundary close to the receiving logic. For location self-parent-child, target insertion port must be on target domain as applicable. Now, tool must error out when it's impossible to insert ISO without port duplication. So, we understand path-based semantics promotes net splitting and discourage to use or prohibits to use port duplication, port splitting. This slide will explain why port-based semantics are ad hoc and how collateral damage could be caused because of port-based semantics. We adopted an example of isolation strategy where isolation strategy is applied on sub-PD. Source is sub-PD.primary and sink is top-PD.primary. We interpret this isolation strategy in the design example shown in the block diagram, where top PD have two different instances. Top PD have two subblock, and each subblock are instance U1 and U2 belongs to sub PD power domain. The output of instance U1 goes to top PD, and also goes to the instance U2 as shown through the arrow lines. Practically, power domain crossing exists only one because instance U1 and instance U2 both belong to sub PD. So practically, the instance U1 output will only be crossing from sub PD to top PD. If we apply port-based semantics, port splitting will infer two different isolation, whereas only one power domain crossing or path exists. So we can see redundancy in isolation insertion, which is a product of collateral damage. We continue to explain path-based semantics in order to optimally manage power on any design. Here in this slide, we adopted an example of isolation, ISO 1, with domain blue and sync green. We have location self, location parent, and location fanout set up in this diagram. So the top right-hand side shows the location self, bottom location parents, and the middle one location fanout. Now let's see how tool can imply isolation based on the strategy and location. For location self, as the power domains are distributed, and because of the self, the strategy will imply isolation only inside the blue power domain. For location parent, the tool will infer isolation just before the path that goes to the green power domains, so that both in3 and in4 ports of green power domains logic belongs to D and E are covered. Let's see what will happen for the case of port-based semantics. We can see that port-based semantics will apply isolation at the output of out1 for location parent. It's still on parent, but unnecessarily setting all the paths covering in1 this glue logic into for orange power domain, in 3 for green power domain, and in 4 for another green power domain. What will happen for the location fan out? Here, tool can implement the isolation strategy in such a way that affects only the target receiver, that the green sinks, as shown in this diagram. Now let's consider another example, ISO2, where domain is blue and sink is orange. Again, we have the setup for location self corresponding to this diagram on the upper right hand corner of the slide, location parent on the lower right hand side, and location fan out on the middle portion of the slide. Now, tool cannot implement ISO that affects only target receiver orange domain because of the condition location self. For location parent, again, tool cannot implement ISO that only affect receiver because it will affect also the green in 3. Let's see what will happen for the port-based semantics. Just like the previous example, the port-based semantics will apply isolation at the output of the blue power domain out1, unnecessarily covering all the paths to the another in1 blue, and the glue logic B in 1 of orange, in 3 of green, in 4 of green. Now let's see what will happen for the isolation strategy with location fan out. Tool cannot implement isolation strategy that only affect target receivers. In this case, the orange power domain is the receiver sink, because it will sit inside the green orange power domain, and it may also cover the path that split it from in2 to in3. Now let's summarize the observation based on our example. It is evident from the case studies that on real design, location self shows similar placement for ISO cell. However, location parent and location fan out, port-based and path-based semantics differ significantly. These differences allow user to comprehend optimal and accurate designation of ISO cell from a very early stage of design phases at RTL, which bounds to comply on down the implementation phases for UPF protection cell insertion, whether it's during synthesis or whether it's in PNR stages. Now we go further explaining path-based semantics, and in order to do so, we need to understand the high-con, low-con perspective of ports in context of parent and child power domain. The path-based semantics applies ISO on ports and high-con side of the parent instance. Now, what is high-con? In this diagram, we have top PD as parent and sub PD green as a child. The high-con side from parent perspective of the square port shown here on the interface or on the boundary of PD top and sub PD is the red one is the high con, and the green one is the low con in parent context. Now let's see how the high con is applied in terms of path-based semantics. We adopted another example. Here the diagram looks a little bit difficult to understand, but let me explain. We have adopted an isolation strategy for domain PDA, which applies to the output. The location is parent, and we also have deep supply only true. please understand that the red instances belongs to PDA and the yellow instances belongs to PD0. The simplified diagram shown on the right hand side of the slide, where PDA is the child and PD0 is the parent context, and we have applied an isolation cell only on the OA which is applies to the output. So set isolation location parent will apply isolation nowhere in the parent instance. Only it will consider the HICON side of the port of the parent instance. That is why the dotted portion of these block diagram doesn't allow to insert isolation cell, and only insert isolation cell on the HICON side of the parent. PD0 is the parent and PDA is the child. In addition, we will also generate a warning message, and we adopted the warning message from the tool we used for experimenting this diagram-based design. Here, the tool generates an error that shows isolation strategy specified on a particular port OA can't be applied without splitting the port. To avoid port splitting, cell will be inserted for the paths that goes to the target receiver supply. In this case, the HICON of the parent power domain. We further go beyond with port path-based semantics in order to easy transition from port-based to path-based semantics. There is always a big concern of ISO placement before a glue logic on a fan-out path. That means if we have a heterogeneous fan-out scenario and we have a glue logic on the heterogeneous fan-out path, whether it is required to place isolation on the glue logic or not. We adopted a methodology and algorithm where tool allows user to allow or disallow isolation before this glue logic. Now, let us consider the example shown on the right hand side. The glue logic is sitting on the top power domain, which is PD1 and always on. The other power domain, PD2, is a switchable power domain, which is the source, and PD1, which is always on, is sink. As we can see, if user has a discretion of enable, disable, and user allows to put an isolation in front of the glue logic or not, depends how and where and which situation will be explained in this diagram. Now, for glue logic, we implicate enable disable option, as we mentioned, for allowing or disallowing glue logic. Let us consider that user specified disabling ISO before the glue logic. It is evident that the module 3 output ports are not directly connected to glue logic, but they are connected to top-level module output ports. Also note that module 3 output ports are not path-based. They are only a path going from out of module 3 output ports. Hence, based on user discretion, tool option to disable ISO before glue logic has no effect on these ports. Such a disabling ISO option will take effect only when port has multiple paths. Corresponding to ISO strategy is not applicable to one of these paths, and port is directly connected to the glue logic. For example, this one. So, we can conclude that based on user discretion, whether isolation strategy will be applied on the in front of the glue logic or not, we see that based on these set isolation strategy where domain is PD2, location is fan out, and applies to the output with diff supply only true, we can see the path-based isolation will be inserted only on the green circle shown here. However, it will not placed in front of the glue logic based on user discretion because of this port, and there will be a message that shows ISO not required. Finally, we come to the concluding remarks. We already explained when and how isolation are required, and if it is not inserted properly on the right path, it can lead to functional failure of the design. In case there is redundancy, it can waste area and consume unnecessary power. We have explained that path-based semantics allows to manage power very efficient and optimal way over the legacy port-based semantics. With the path-based semantics incorporated, the tool insert ISO LS repeater closest to and connected to the target insertion port within the extent of the location domain. For ISO level shifter repeater cell strategies, if users specify -sync in the strategy, then the inserted cell affects receivers that are powered by the supply set that matches the specified supply set. For ISO, if users specify diff supply only true, then the inserted cell affects receivers that are powered by the supply set that does not match the driving supply set. So sync, source, diff supply only directly manipulate location. And as we know, UPF 3.1 specifies the path clearly on which isolation, level shifter, and repeater must be applied. However, in case if these semantics and algorithms are not implemented or incorporated in a tool in proper way, then the tool should error out with appropriate messaging for the user. With these, I conclude, and this slide shows the references which all comes from the different version of the LRM spreaded over from 2009 to 2018. Thank you, and open for the question from you.
Hey, Progyna, great presentation and very nice observations, and you have captured it really well. So we have the first question from Brandon. You can just answer it, right?
Yes, thank you. Thank you, Rohit. Can you hear me?
Yes, very well.
So, Brandon, thanks for your question. Yes, at the bottom line, the LRM does not allow you to place isolation before an glue logic. But it happens that one of our customer wanted to have this isolation strategy in front of glue logic, despite the 3.1 LRM does not allow. So that's why we allow enable disable condition, and also showing that error message that this is unnecessary and could cause potential redundancy or functional failure. So did I answer your question, Brandon?
Yes, I actually didn't understand that the LRM forbid it. So you're saying this is something that you added for a customer requirement, but you're warning them heavily that this may not be a good idea. Is that what I heard?
Yes. Yes.
Okay.
So basically, looking at the port-based and path-based differences, the path-based do not allow to have an isolation strategy because of the example that I have shown. Because it is unnecessary. If you have a source and a sink and you have multiple paths distributed from source to sink, it's okay to have multiple isolation. That's the common idea of path-based. But if the path is only one, then only path means in the boundary crossing between domain A and domain B, source and sink, where source is A and sink is B. then it's sufficient to have a single isolation that I showed in the previous green and orange examples.
Right.
So the bottom line is that isolation may be not necessarily required when based on your source and sink condition before an isolation, glue logic. But if you want, we have an algorithm to implement that. But also it heavily warn you, of course, that it may be causing redundancy or could cause functional failure if you do not properly, assert, enable, disable of these isolations.
Perfect. Thanks.
We have another question, Progyna, please.
If you have different crossing, then each isolation strategy will be applied to each. So there would be no collateral damage. There would be no single isolation strategy when you have multiple crossing between domain A and domain B, Dipankar. So you have to have separate isolation strategy, and then isolation strategy would have separate clamp values.
But if the crossing is same,
if the crossing is same, there is only one isolation strategy should be sufficient, and one isolation cell would be placed. That is the beauty of the path-based semantics.
no, but if there are some signals which we want to put the clamp value 1. So generally we explicitly have to write a separate element-based strategy for those signals, right? How do we take care of
clamp value? When you say clamp value and when you say element, I do not understand the correlation. Element is how you filter the number of elements in your design from a point A to point B. And clamp value is the value that you want to clamp your output during the power shutdown from the source to the sink so that X doesn't propagate. So there are other strategies that where you can have, multiple isolation, multi-control isolation. You can take a look into LRM. So single isolation strategy could have multiple clamp values. So that is a different scenario, not related to the path base.
Thanks.
So I have one question. So Progyna, in the cases, right, based on your learning on the path-based, is there any from the UPF 3.1, is there a standard guidelines that what is the best combination, whether it is a diff supply, location fan out, or applies to output? Is there a combination which works fine for most of the cases?
Yes, that's a very good question, right? So the bottom line that provided by UPF 3.0 LRM is that you have to have a sink. So in your isolation strategy, you have to apply, you have to have this sink declared. And then it is easy for the tool to analyze the source sink analogy and place the isolation towards the receiving side of the power supply. So receiver power supply would be powered for this isolation and would be placed towards the receiver side. As I mentioned multiple times in the presentation, that path-based methodology adoption has issues when it depends on the contents of your strategy. That means if you have location fan out, location self, location parent, it may cause additional complexity. So in order to answer your question, the minimum requirements that UPF 3.1 gives on the path-based semantics is that you have an isolation strategy with dash sink and diff supply only true. If you have these two, the tool is bound to make the isolation on the path, not on the port.
Sure, thanks. All right, so I think we are out of time. Let's get into the next presentation. So the topic of the next presentation is problematic bidirectional port connections. How well is your simulator filing the UPF LRM void? filling the UPF LRM void. And the presenter is Brandon Skaggs from Infineon Technology, and he's currently employed as principal CAD engineer at Cypress Semiconductor, an Infineon technology company, and he's focusing on front-end design and verification methodology and low-power platform-based integration flows. So over to you, Brandon. Please play the recording.
Hello, I'm Brandon Skaggs from Cypress Semiconductor, an Infineon Technologies company, and I'm here to present Problematic Bidirectional Port Connections. How well is your simulator filling the UPF LRM void? For our agenda today, we'll spend a few minutes reviewing the motivation for this investigation and what I hope to contribute by presenting my findings. Next, I'll present some common bidirectional port issues that design and verification teams commonly encounter during power-aware verification with UPF. I'll then discuss 3 approaches that can be used to model bidirectional ports during functional power simulation. Next, I'll discuss my test setup, the test cases created for study, and the results that each of 3 commonly used EDA functional simulators produce for each. Finally, I'll present my analysis and some concluding remarks. The UPF LRM does not describe in detail the handling of bidirectional in-out HDL port connections, leaving this open to interpretation of EDA tool vendors. Bidirectional HDL ports are discussed in the UPF language reference manual, but details on how connections of these ports to UPF supply nets should be modeled and resolved are not fully discussed. How tools interpret proper behavior of bidirectional port semantics can have an impact on best practices for designing hierarchical power intent and writing effective models for simulation. An understanding of how contemporary commercial simulators handle these ports can inform best practices and possibly suggest improvements in future IEEE 1801 revisions. To that end, the goal of this paper is to present a systematic survey of the behavior of 3 contemporary power-aware digital simulators, investigating how each treats common bidirectional port scenarios. To reach this goal, this presentation will discuss 2 common bidirectional supply port modeling scenarios, one involving HDL to supply port connections and one involving hierarchical in-out supply port connections. Present 3 methods for modeling bidirectional connections, methods that are often used to work around the ambiguity of what the resolution of such connections should be, and review the support of each method by each simulator. Present the test cases we designed for this investigation. Finally, review the test results, general observations based on the results, and suggest ways the UPF LRM could be updated to make bidirectional connections less problematic. Let's begin by examining 2 common bidirectional port modeling scenarios. Scenario 1 is the common scenario where a macro verification model describes one of its supply ports as an HDL in-out port. The system UPF makes the connection between a system supply net and the Module M instance's in-out port. However, it's not clear from the connection itself, is Module M being powered by the system supply net, or is Module M supplying power to the system via the port? Section 6.19 of the UPF 3.0 Language Reference Manual states that the high con of an in-out port is both a source and a sink, so the presence of this HDL in-out port implies the possibility that M could drive the supply net. Scenario 2 is an example of a hierarchical supply intent definition, where multiple design objects, Module A, Module B, and subsystem in this example, are all parallel drivers of the system supply net VCC switch. While the definition of what parallel supply net resolution should be is well known, i.e., the net VCC switch should only appear full on once all sources are full on, this is difficult to achieve at the system level because some simulators do not support the in-out supply port definition that would be required to allow the subsystem to be a parallel driver of the system supply net. In such cases, verification engineers must be creative and work around these limitations to produce the functionally equivalent modeling of what the system really is. Let's look at some of the tools and modeling approaches that verification engineers can use to overcome the modeling uncertainty of bidirectional supply ports. Probably the most common way of handling HDL in-out connections during power-aware simulation is to use compiler directives to select input over in-out direction for nets that are truly or not meant to supply power to the instantiating system. This behavior is well defined. However, these models are not often written with this objective in mind, so this approach only works if the underlying model can be updated as desired. Another method for resolving problems stemming from bidirectional supply ports is to use the resolution function capability within the UPF language. Several built-in functions are provided for common resolution situations. Unresolved supply nets expect only a single connection and resolve to undetermined if more than one source is connected. One-hot supply nets allow multiple drivers, but if more than one are active at a given time, the net resolves to undetermined. Supply nets with parallel resolution allow multiple simultaneous drivers and are considered full on only if all sources are so. Parallel one-hot resolution allows for only one active root supply, but requires that all derived supplies be on before the net is on. For more complex interactions, a system Verilog function can be defined for the supply net to resolve it in a custom way. This provides a path to handling problematic bidirectional source ports by giving precedence or higher weight to one of a set of driving supplies. The function shown is an example of a custom resolution function as it appears in the UPF 3.0 language reference manual. This function sets the supply net state to full on if any single source is full on, but allows more than one source to be fully engaged. Custom resolution functions are helpful because they're well defined since they are written in System Verilog. However, they are only available within the UPF 3.0 and newer revisions of the UPF language. Also, since UPF supply nets have only a state and voltage field, there is no inherent way to identify one supply net from another within a custom resolution function. In other words, there's no name field reference, so any custom resolution functions meant to show precedence or preferential treatment of one supply over another must keep track of arguments positionally. Rather than use the UPF provided resolution functions, supply nets can also be resolved in HDL directly by intentionally removing or omitting the normally resolved UPF supply net connection, including within the test bench code that is bound in that resolves the various HDL sources using HDL values and signal strings to a single HDL resolution, and then connecting the resolved HDL signal to the UPF supply net within the UPF. In this example, 3 sources drive VACT custom, but the goal is to model VACT custom equal to VDD out from switch M if it's active. Otherwise, require both switch 0 and switch 1 to both be active before VACT custom is active. To accomplish this, we write a custom function to resolve this using Verilog. We then bind this in via the test bench, interposing the connections between the switches and the bound module, and between the bound module and VACT custom within the UPF. From the waveform, you can see how VACT custom is full on whenever switch M is on, or if switch M is disconnected, high Z, VACT custom is full on only when both switch 1 and switch 2 are on. Having described the key concepts, let's now turn our attention to the specific test cases evaluated. The first set of tests are for evaluating the default behavior each simulator has when dealing with scenario 1 and 2 discussed previously, with variations to test how bidirectional signals are evaluated when used functionally as inputs or outputs within the circuit under test. The second set of tests check each simulator for compatibility with the 3 methods for modeling resolution, a useful feature when bidirectional port behavior is problematic. In scenario 1A, where bidirectional ports are intended as inputs, all 3 simulators performed as expected. HDL in-out ports used as inputs were correctly resolved as such, and the macro model was powered from the connected supply net. For scenario 1B, where the in-out HDL signal was expected to drive the supply net, only simulator A modeled the expected behavior. Simulators B and C, however, both retained the same behavior as scenario 1A, expecting the bidirectional HDL signal to be an input to the circuit. This left the signal undriven within the macro model. Recall that scenario 2A describes a hierarchical power intent specification where module A, module B, and a switch within a connected subsystem all contain HDL in-out ports, and these ports are all driving supply nets that are described with parallel resolution, connected via a UPF supply port declared with in-out direction. In this scenario, the expectation is that both the system-level supply net and the subsystem-level supply net should function as one net with parallel resolution. Scenario 2A, testing hierarchical UPF descriptions with bidirectional HDL ports, could only be done with simulator A, since, as discussed in the previous slide, simulators B and C would not allow HDL bidi ports to drive a supply net. The results from simulator A matched expectations. While the simulator warned that BiDi UPF supply ports were not supported, it appeared to model the correct behavior anyway. The top-level supply with parallel resolution was full on only when all supplies, including the hierarchically driven supply, were on. The submodule supply net followed the system-level supply net, as we would expect from an in-out port connection. In order to more fully test bidirectional port behavior with UPF supply nets, scenario 2A was modified to avoid the in-out HDL port issues that prevented it from being used with simulators B and C. The bidirectional HDL ports that were modeling power switch outputs were changed to unidirectional outputs. This allowed all three simulators to be tested to determine how the parallel supply net shared between the system and subsystem, connected via the subsystem UPF port, would resolve. For the first iteration, the UPF supply port was declared to be in-out. System-level supply net VCC switch has three drivers. It should be partial on when any one is on, and only full on when all three are full on. As a parallel supply net connected via UPF in-out port, subsystem level supply net VCC switch subsystem should exactly mimic this behavior. In the second variation, the UPF subsystem supply port was declared as an out instead of in-out. This creates the expectation that while the three drivers modules A, B, and the subsystem driver US1 should factor in the resolution of the system level net VCC switched, the supply switches from A and B should no longer factor in the resolution of the subsystem level. The only driver on VCC switch subsystem within the subsystem is the switch US1. Consequently, we would expect the subsystem net to be full on whenever US1 is full on. In the third and final variation, the UPF hierarchical port was declared as an input. In this configuration, the subsystem switch state should not affect the resolution of the system-level supply net VCC switched. However, the subsystem supply net VCC switch subsystem should see the same drivers as in scenario 2A, meaning it should only resolve to full on when all three drivers are full on. The results showed all three simulators modeled proper parallel net resolution at the system and subsystem level whenever the hierarchical UPF power port was declared as an in-out port. However, all three simulators exhibit slightly errant behavior based on what we would expect from the UPF LRM. All three simulators exhibited the same behavior for the system level supply net, resolving it as expected to be partially on when any one source was on, but only full on when all three were on. When the UPF port was declared unidirectional, all three simulators behaved slightly differently and all varied from expectations. When the UPF port was declared as an output, simulators A and B still showed the subsystem supply net going partial on due to changes in the downstream or system level supplies. The subsystem net behaved as if it were still connected via an in-out port connection. When the UPF port was declared as an input, simulator A never fully resolved the subsystem supply net as full on, even if all connected supplies were full on. Simulator B mapped the state of the supply nets based on the state of the parent domain and not the state of the connected power ports. Finally, Simulator C treated all three UPF port declarations, in, out, and in-out, as the same. Now let's review the results of the modeling test cases. The first approach, using compiler directives to change port direction, was well supported by all three simulators as expected. The second modeling approach, using UPF resolution functions, was supported but somewhat unevenly. Only simulator A supported the IEEE 1801 example resolution function as written. Simulator B only allowed custom resolution functions considering two supply nets, and then only when declared within a task. Only allowing two supply nets is a significant departure from the UPF command syntax that places no limit on the size of the TCL list that can be connected. Simulator C only allowed extended resolution of supply nets using tool-specific extensions of the UPF, and within these functions the resolution options available were limited, not whatever is generally supported by System Verilog. The third and final approach, using HDL resolution to resolve supply nets, was more well supported. However, there were some unexpected limitations. Only Simulator A supported HDL resolution on nets defined and connected within the UPF using create logic net and connect logic net UPF commands. Simulators B and C required the HDL nets to already exist within the HDL definition. This limitation seems out of sync with the UPF LRM, and the need to modify the source HDL limits the usefulness of this approach for verification. So what should we take from this exercise? Let's look at some analysis and conclusions. The UPF HDL resolution vectors, VCT, do not seem to be used for resolving supply net drive direction, in spite of the fact that they're written and applied with a source destination in mind. Simulator A was the only simulator to allow bidirectional HDL ports to be connected and used as outputs. The other two defaulted the ports to inputs in spite of the context of what they were being connected to. It was also the only simulator to fully support the example IEEE 1801 custom resolution function as written, and it was the only simulator to allow binding connections with UPF provided logic nets. UPF custom resolution functions are difficult to apply because supply nets do not contain a name or ID that would allow a user to distinguish between a set of supplies to resolve. The resulting supply sources of supply net type appear only with state and voltage information, and the UPF LRM does not provide an explicit definition about the order the supply net connections are maintained when multiple connect supply net commands could each make multiple supply net connections each. It would be difficult to write a custom resolution function without the ability to identify signals by name or with some clear definition for how signals connected via multiple connect supply net definitions should be ordered. In conclusion, the default treatment of in-out HDL ports and UPF hierarchical port connections vary across EDA vendors, and basic support of common bidirectional port modeling functions is uneven across the three major EDA simulators. Furthermore, future UPF revisions should seek to take advantage of VCT drive direction information to determine which side of a supply net is a source. Finally, future UPF revisions should make this ordering of resolution function supplies explicit, or future supply net type definitions should include a name field that's populated when nets are declared. This concludes the presentation. Thank you for
Hey,
your attention and for your patience with us in this virtual format. I'm sorry I won't be able to join you at the bar after the session for questions, but feel free to reach out to me via the contact information that the conference has provided. And now I look forward to a live Q&A session.
hey, great presentation, Brandon. So indeed, you have touched upon some of the gray areas in UPF LRM and how simulators are actually behaving differently. So we have some question. You mind answering them?
Not at all. Let me see. I've got the chat window. This is from Progyna. Question is, when Sim B and Sim C fail to properly behave with the N out, do you think these simulators are missing resolution function VCT or just missed bi-port functionality? Are you talking about with handling the HDL models, the models with the HDL ports?
Yes, Brandon. So the bottom line of the question is that do you see that the simulator that doesn't allow you to do modeling in output properly is that they fail to manipulate or implement VCT properly, or just that they're following LRM very strictly?
It's a good question. I know that I did explicitly provide VCTs in all these cases because I wanted to make sure we provided all the information that we could. But from what I recall, and there was a direct messaging in the log just saying we don't allow this behavior. So I don't. It doesn't look like it was a failed to implement. It was we're not going to, because it's not defined. We're just going to pick a well-defined behavior and stick with that.
Thank you.
But as I quoted in the presentation, I do believe that the presence of that in out from the LRM should imply that it could go either way.
Right. Thank you.
So yeah, I also asked one question regarding this. When we have this bidirectional port intended to be output, right? Some simulators saying it's a undriven port or something. So there is no clear guidelines on how the source or sink behavior should be available here.
Well, from the connections itself, the best information that I think is there is in the VCT, as I say in the paper. If the from one macro model to the other, as far as the language is concerned, there really is no, at the interface level and the connection to the supply net, there's really nothing that can be inferred without providing something like a resolution function, a VCT function. I'm not sure how really the simulators do that. Progyna could probably comment on how the tools do that, but it does look like that there's some interrogation to figure out if there's a driver, for example, on that net, and then they would imply a driver onto the supply net. But obviously, that's the one simulator that actually could behave that way was what I was seeing. So I don't know if that answers your question, but to me, the VCT information is the best information.
All right. So we have another question in the chat window.
Yeah, the question is, did you contact vendors B and C indicating the desired behavior? Not yet. Actually, I'll be completely honest with you. I'm working in a house with the versions of tools that I have on hand. The versions that I did use are not the latest, but we're talking about a spec that was finalized in many cases. 2009 was when many of this stuff was in place. So I did want to withhold filing tickets until I had a chance to try it on the absolute latest versions, but I haven't had a chance to do that yet. But I would, if we were all in person, I would have loved to sit down and find the various folks. And I've sworn myself to secrecy. I'm not going to name who A, B, and C are, but if anyone wants to reach out to me from those companies, we can have that conversation.
Brandon, just a quick question. You mentioned very clearly and summarized very excellently at the end, like you have suggested to have a proper VCT connect supply net and also in-out port direction. can you please let me know your thought that how we can take this message to the IEEE 1801 committee? What is the ultimate message that you want the committee should focus?
It's a good question. What's the way to distill this down into a requirement? I think the VCT. I think inferring whatever information is there from the VCT, because I know many of the tools will warn you if you inadvertently apply the VCT in the wrong direction. So they definitely can tell as if you're mapping from supply net to HDL resolution or vice versa. I think there's a good understanding of what the intent is there, and if you get it wrong or if you mismatch what the connection is, I think probably the best requirement for that is use whatever information is there. The harder one is when it comes down to these custom resolution functions. I don't know what the answer is. Those supply net supply net types have been around for a long time. They're widely used, and obviously if a person wanted to create a name field or some other custom type in all of their code, instead of using supply net types, they use some other extension of that, they could. But it seems to me there are more people involved in updating what the default supply net type object is, and how that, and what the behavior would be expected when you create that, how those fields would get populated. I'll have to give some more thought to that, what specifically I would ask for. I think if you gave me a blank check, what would I want?
Yeah, I mean, it's not really the blank check. You have given very clear destination, direction for the LRM. But I just wanted to focus more because we extensively support VCT and the directions. We might be losing some of the connect supply net information that you have identified. We can discuss or in offline. But overall, I really appreciate it. This is a very wonderful presentation. Thank you.
Well, thanks, Brian. I appreciate it. Any other questions?
No, there are no other questions. So I'll just request all the audience, please go in the voting section and just vote for the best papers and all. That would help, defining the, or rating the best paper. All right. Okay, so if there are no further questions, thanks, Brandon. It was really great insight. Thanks a lot. And this is where we end the session.
All right.
Okay.
Thanks.
All right. Thanks,
thank you,
everyone.
Rohit, and thank you, everyone.
Thanks, Progyna. Thanks, everyone. All right.